All right, so I know at least one of you already got it. Let me see. You got any idea? You should show the valence electron.
See? It's right, doesn't it?
All three of these are not resonance to each other. They're all the same. I think the problem is that you moved the double bond, but you didn't
Actually, you should
create
this one.
hydrogen electrons. So you ended up breaking the octet rule. Yeah, you have all three. Okay, so first let's discuss how to properly draw CO3 2 minus. The basic way. How many valence electrons does oxygen have? 6. And carbon? 4. And so if we use our original method of drawing the Lewis structure, we would get this. And then where do the 2 extra electrons go? We put them on any of the 2 of the 3 oxygens, right? So I'm going to put 1 here and 1 here. Then I start making bonds. Bond here, bond here. And then here, I'm going to move one of my electrons down. Do you remember we should probably use pencil for this? Move one of my electrons down here. And then this becomes a double bond. But the double bond didn't have to be there, right? So this is one resonance form. The resonance form says that this double bond could have been over here, or it could have been down here. Those are the 3 different variants. So you would then draw this and say, okay, so I know that the double bond could have been there, or it could be here. How would that affect oxygen's electrons? Would this have 6 valence electrons now or no? Because it had 6 here. Would it have 6 here? Would it, like, would you put the 2, 2, 2 there, like 2, 2, 2 there? No. It would be 1, 2, 3, 4. Basically, whatever it looks like on this side, that would be transformed to that side. So that you're still fitting octet rule for all the elements that have to follow it. You're just moving the double bond around. And I checked one person who they didn't show the valence electrons, but they showed the formal charges. And that's communicates the same thing as writing the correct amount of valence electrons. And then where's the other spot where the double bond could have been? At the bottom. But this time you'd have to write, instead of 6 electrons down here, you'd have to write the 4 down here. And then here you'd have this and this. And those are the 3 resonance structures. So this is a good resonance structure because this is a -1 and a -1 charge. This is 0 and 0. So you've got a low charge separation. Every element that has to fit the octet rule does. And the elements that are supposed to have the extra electrons that are the most electronegative do. So I want you to now think about a second one that I didn't write in the lesson, but I wanted to address it. What would be the best resonance structure? What is the best structure for SO4 2 minus? I know I printed these 2 on purpose, like I put these 2 per slide on purpose. See if you can try to figure out what is the best structure for SO4 2 minus using what you know about formal charge, like the rules for formal charge. Meaning, follow them. What is the major contributor to resonance for SO4 2 minus? I want you to think about it. Try drawing it up. See if you can come up with the best resonance structure. And there's a couple variants you can come up with. This is it. Yes, you got it. Raise your hand if you want me to check. I'm going to give it a couple minutes before I start going over what it would be and why. You have it. That's it.
Isn't that like the only possible?
Well, I mean, you can do them side to side, but yeah, it's the same idea. Yep. Yes, it is. Correct. Either that or you can write the form of charge of heat.
I know what it's.
Yes, that is the best. That's true here. Yes. Okay, so everybody who I checked got it. Yay. The best resonance contributor, the major contributor, would be this. And you could either write the formal charges or you could write the valence electrons to prove it. The formal charges are -1 on the two oxygens that have the single bond. So that gives you the lowest charge separation. What would have been the problem actually with this one that technically would fit the octet rule? What's the problem with this one if we had done this instead and we did this? Because this is technically, it's a resonance contributor, but this is a minor contributor, not a major. This is a major. Ben Como, yes.
Sulfur has 6 valence electrons. Since
So
it's
gives
only
us
single
+2.
bonds there, you just do left the end.
So this one would be like this. So you have a much larger charge separation because you've got everything that has a charge. Whereas your best, interpretation of the molecule is the one that has the best distribution of electrons that gives the closest to what the element's supposed to have. Yes.
What does resonance mean then?
Resonance means that this double bond could have actually been there or there. That technically, or that these electrons could actually be right there.
Okay, I get it.
Like they could either belong to the oxygen or they could be shared between the two. And here, these electrons could have been there or there.
They're like the most.
So the most stable variant is the one you see it existing as, which is the one is this one, is the major contributor.
Okay.
That make sense?
Yes.
All right, so I think I took this out. All right, so we're moving on to benzene history because I want to do the SO42 minus 1. Benzene history. So in the textbook, there's a little bit about the history of benzene. It's a kind of a cool history. They're not really going to ask you any history questions from Cambridge, but what they could ask you is how the bonding is in benzene, and this gives a little bit of a background. And so chemists knew what benzene was before they knew its structure. They knew how it reacted. It was used for a lot. It's actually cancer causing. It's a carcinogen. But so before people knew, the health side very much, they just came up with all these chemicals and used them all the time. And then there was a lot of, health issues that occurred as a result. And in this past century, we've gotten caught up on the health side of things. We're like, well, maybe you should use precaution while using these chemicals. And so it's a volatile liquid because it's nonpolar. And it's used as a solvent a lot of times for organic molecules, but it's definitely insoluble in water. So you could use it when shaking your two layers for partition coefficients. There was, talking about that, I think so far, there's still 4 people that haven't taken the test yet, 4 or 5. But out of the ones that did, I think there was a total of 1 person that got the partition coefficients question completely right. I don't remember. I have the test at home. But a bunch of people got the definition right, which is worth 2 of the 4 marks.
Yeah.
Anyways, so chemists used to use it with few precautions, but we know it's highly toxic now. It's a carcinogen. You can go to the CDC website to see what exactly it does. They have a whole list for every chemical, what its issues are, known health issues are. So in the 1800s, they actually were able to work out that the molecular formula for benzene was C6H6, so they knew its molecular formula, but they didn't know how it was structured. They were like, well, how do we get 6 hydrogens on 6 carbons? Because typically, you follow the CnH2n + 2 rule, and that would be C6H14. And so they're like, it doesn't make sense. How do we get to this? And this was actually something that they worked on for decades. They were trying to figure out what is the structure, what does it look like? They knew what it did experimentally, but they didn't know what it looked like. So they thought that it was a straight chain structure for the longest time. So what would you think if it was a straight chain structure? I'll let you think about it. Like this is what they went over, and they were like, what? Why? What is going on? Why doesn't it react like this? It would be something weird like that, yeah. It has to be C6H6. But they found that it reacted different than other alkenes. Like its reactivity was different. So they were struggling. So just think about it. What would you get? It has to have, 4 carbons, the 6 carbons make 4 bonds, and hydrogen makes 1 bond. So what would you come up with? You're kind of looking ahead.
No, yeah, the thing is, there's a lot of memes about this guy and the whole he had a dream about it thing.
Oh yeah.
People joke a lot about how do you cite a dream in MLA format for the paper.
Well, you should,
When did MLA format start though?
Still, you know,
I
like
think,
what do you
I
do?
think he predates MLA.
Yeah, of course, but it's very
format.
funny.
I'm pretty
Just
sure.
Like imagine that citation. I had a dream about
That I'm
this.
not sure of how you APA format this.
oh,
That was one thing we were joking about, like how do you cite yourself? Like
Yeah.
if you came up with the idea. That works. Yeah, you
I
can
mean,
do
you
that.
just write an academic paper on the dream, and then
So
you
this
publish
is just
it,
a
and
thought
like
This guy's like going
cite yourself in
insane.
the academic paper.
APA.
Right.
He dreamt that the benzene molecules were
That's how
When
you
did
do
APA come about?
You cite the dreamer, the day, and the description of the dream.
Okay.
You're lying. Actually,
That's
there's
APA
an
format.
actual format for citing dream. That's awesome.
Citing dreams.
What about hallucinations? Is there one for those? Is the same?
Yeah, it's hard to see. So I saw several different answers that you all proposed. Some with like 2 triple bonds, some with 4 double bonds. None of them were right? None of them were right because it's not single. Benzene is not a straight chain. But that's what they were working on. So a German chemist, and I want to say it's pronounced Piccoli, but it may not be. You can look that up. He had a fortunate dream. I think that's how they worded it. While trying to solve the structure, he dreamt that the benzene molecules were snakes that bit their own tail. And that's how he came up with the structure of benzene. Instead of it being a straight line, it was turned over. And the dream inspired him to propose his structure of benzene, which we now use now, the common one with 3 double bonds.
Correct pronunciation. Take it away.
Yes. We have already done this, so skip.
How do we know that that's correct?
So with the techniques and the technology that we have now and computational chemistry, we know that all the bonds are the same length in between, so it has to be and the way it reacts. It has its own unique set of reactions. So hundreds of years of experimentation have proven that his structure is the accepted one.
It was a
That's
super
what it
dream.
is. He had the best dream ever. So we use it for so much, or derivatives of it. We use them for so much. We use derivatives of benzene for medicine, or dyes like your colors, food coloring. For many plastics do use benzenes in them, and it's not necessarily cancer causing when it's part of other compounds. It's just the pure benzene itself. Somebody's phone is possibly going on, or I don't know. We can move down. Anyways, it has so many important usages, and you're going to see those usages later on in this unit. Yes, you will see a bunch of them. We have to actually talk about dyes. There's a whole lesson on how common dyes are made because they're like a class of compounds with benzene. Some of them are cancerous. A lot of them have been out, or potentially. Some of them have been outlawed in California, specifically, like some of the clothing dyes that are used. And we'll talk about that later on in the unit. So aromatic compounds are also known as, you can almost think of these as synonyms. Arenes are hydrocarbons that have 1 or more benzene rings. We also call them aromatic compounds. And aliphatic compounds are ones that are just straight chains, open chains. So there's arenes, aromatics, and then there's aliphatics. And then Cambridge doesn't really use that terminology very much, but just so you're aware of it, like if you were to study more organic chemistry. But you do need to know our rates. That was actually one of the things I ended up putting on the test, but you could have just said it with benzene. They accepted that. All right, so more here representation of benzene. Okay, pulling structure suggested. Go ahead, Daniel. Is it full?
The oldest citation format is Chicago, and he missed it by 40 years.
By 40 years.
Well, I guess you didn't have to deal with that struggle, but
You didn't have to deal with it.
Actually,
But that's an interesting thought.
yeah, like
Like how do you cite your dream?
how do you set yourself
Wait,
in
wait,
anything?
Daniel, what about Isaac Newton and the apple?
All right.
How do you
So
set an apple falling?
That didn't happen, so we don't have to worry.
Kikune wasn't completely right though because he suggested that there were 3 double bonds and 3 single bonds, and this would suggest that there were different bond lengths in the molecule, and there are not. In the experimentation, they found that all the bond angles between the carbon-carbon bonds are all the same, which means that resonance is at play. That this double bond could be here, could be here, could be there, could be there, could be there, could be there. The electrons are delocalized.
Yeah.
Is the idea. The pi bonding
That's
electrons,
true.
it makes a system like,
My bad.
remember this?
You're right. You're right. My bad.
Like all of these next to each other would all be like that. Remember how I wrote the above and below? It would all just go like that, which is how they came up with the circle. Is that all the pi electrons are all throughout the structure. And so the measured bond length that's been proven by experimentation is that the bond length is intermediate to that of a single and a double bond, which means that it's all the same. This also gives benzene unique property that it does not react in the same way alkenes do. So it does not do traditional addition reactions. So if I presented a benzene ring like this and Br2, it'd be like, no, I'm not doing that. Like, it would actually be no reaction. Whereas with a regular alkene, if I presented an alkene with Br2, it's going to become that. So, because the benzene ring is more stabilized, it actually, you have to have more unique reactions for it because it doesn't do the traditional addition reactions that alkenes do. And that's what our next week is going to be focused on is, well, if benzene doesn't do the regular alkene reactions, what does benzene do? What are the unique reactions that benzene does instead? So on the next slide, we're going to see a more thorough explanation of benzene structure. I'll pause.
Actually, he only missed it for 25 years.
Only by 25 years? Not bad. They had asked that bond order question for this one. I think it would be the carbon-carbon bonds would have been 1.5 because it would be halfway in between because they did it for carbonate.
He was old enough to have used Chicago South.
How old was he when you drank this?
He died at 66 in 90s.
66? Come on. Just live one more year.
Okay. All right. So the structure of benzene is explained by considering its bonding. And the thing you have to remember is this. So you have to remember that the pi orbitals are spread all over the carbons, which I kind of already mentioned. You should also know that you have sp2 hybridization all over benzene. I think that's not really visible.
35.
He discovered it at 35. Okay. Not that old. So he lived 31 years after.
Did you get bitch?
Doubt.
Bro.
All right, so you do need to know that benzene is sp2 hybridized, and that means that every carbon has a double bond, which gives you this pi bonding system of electrons. So you got the top and the bottom with the electrons going above and below, and that gives you the delocalized electron structure. So that's what they want you to know about benzene. The next thing is naming. I know you're so excited to name with benzene. So you do have to know how to name simple molecules of benzene. For most of them, you just end with benzene at the end of the name. And so it's very similar to cyclohexane, but instead of saying cyclohexane, you say benzene. They're not the same thing. And some people on the last test had benzene and copied it as cyclohexane without the 3 double bonds or they're not the same. Cyclohexane does not have double bonds. Benzene has 3 double bonds with a ring in the middle. And so this right here is just chlorobenzene. So if you've got a group like a chloro group, you just write it in the front. Why don't we have to say what number it's at?
Because it could be like the same.
Like they don't start and end, right? So wherever your group is carbon 1. If there's only one group there, so you don't put a number. Here, this is called nitrobenzene. So the nitro group is NO2.
His biggest theory to help him prove that was because of this, that it didn't change no matter where it all gave one isomer. That it wasn't like one or
Because
two,
it's just
3.
one.
Yeah.
Because it's just one thing. It's just one molecule. That's
So
interesting.
it's saying that all carbons are equal.
So there aren't isomers of it. That's an interesting fun fact question too. How many isomers are there of benzene?
6 or 7.
Oh. Phenol. So this actually is benzene that takes an alcohol, takes its own name. So this is called phenol. I've mentioned it before. I'm gonna re-mention something I said about it in the last lesson that's gonna come back important again. Do you remember if phenol is acid or base?
Acidic, right? A little bit.
Actually acidic.
Opposite.
The H plus leaves. Because the O minus actually forms part of the conjugation with the ring, the H plus can leave. Phenol is actually acidic in comparison. There was an order if I gave you last time, and we'll go back into this in detail on another day, but it was alcohols are slightly basic, then you have water, then phenols are actually slightly acidic. That's something that you will need to remember later on in this unit. Phenols are actually way more reactive than regular benzene. That's why we use phenol a lot. And you'll see when we get to reactions, there'll be a whole chapter actually on reactions of benzene and another whole chapter on reactions of phenol. That's how important the phenol molecule is. And so then there's methylbenzene, which actually has a much more used in America common name. So this is the British and, IUPAC official name, methylbenzene. The common name, I think it's important you be aware of it. You're going to study any future chemistry because this is what you would see labeled on a bottle. You wouldn't see it labeled as methylbenzene. They would call it toluene. It's called toluene. That's methylbenzene.
Well, I'm done with chemistry after this chat.
Then you don't need to know it. But if you ever watch Spider-Man No Way Home, they bring it up when they're in the lab. They pull out the bottle and they bring up toluene. So I'm like, I need the toluene to make the webs. If anybody's ever seen, if you watch Spider-Man No Way Home again, I always hear, I catch the chemistry in movies. Yeah,
It's like
toluene's there.
it's like PTSD.
No. There's phenylamine. We'll call it phenylamine. It actually has its own common name. You'll see it less often, but it's called aniline. Is its common name? That's how Americans and people around the world study it as that, aren't using the IUPAC system. And then here you've got some variations to naming. This one is 3-bromophenol. So if I've got phenol, that has to be carbon 1. So this would be carbon 3. So if I've got a substituent, it has to be counted from the phenol. Same thing with methylbenzene, toluene. You would count carbon 1 from the main one, from the main group. And then here, this is benzoic acid, which is also acidic.
Oh, I get it. This is a.
Benzene with a carboxylic acid, so it's benzoic acid. All right, so let's try a couple questions. Lucky for you, benzene does not need to be written in any other form except for skeletal for Cambridge. Cambridge does not require you write benzene in displays. You can if you like, but it's often better written in skeletal because that way you write the circle. All right, so draw the skeletal formula. For 135, try bromobenzene. 135, try bromobenzene. What has to go in the middle? That's to do it like this. And then where are my bromines going? Where's carbon 1? Does it matter?
No.
No. If that's 1, then this is 3, and this is 5. Does it matter if I count clockwise or counterclockwise? No. You're the artist. You do what you want to do. 1,3-dichloro-5-nitrobenzene. Where do you want carbon 1 to be? Sure. So 1 would get a chloro. Do you want to go clockwise or counterclockwise? Okay, so then that's 3, and then this is 5. Like, it doesn't really matter.
Could you have also said that was 1,5-dichloro-3-nitrobenzene?
No, because these are alphabetically the lowest, so they need to get the lowest number possible. Like in that scenario. 3-methylbenzoic acid. So here, if I say that I'm going to put my benzoic acid here, then I could either put the 3-methyl where or where. If this is 1, where could my methyl be?
Take a space apart.
It has to be spaced at least 1 more away. Like there has to be 1 carbon in between. So it could either be here or it could be there. They're the same thing, right? So counterclockwise would put it on the left-hand side, clockwise would put it on the right-hand side, but it doesn't matter. Yes.
Is nitro like the thing that you put in cars to make it go faster?
Nitrous, like nitro boost. It's similar, yeah. Because it's got the nitrogen and the oxygen, yes. All right, quick checkup. Give the number of electrons in the pi bonding system for benzene. How many electrons is it? Six. Because remember, benzene has 3 double bonds alternating, and those are your localized electrons. So it's 6 total electrons in the system, in the pi bonding system. All right, so what do we mean by delocalized electrons? What does that even mean?
The electrons can.
They move on.
The electrons move through the structure, right? At least the pi ones. And so how would we compare that bonding versus hex 3D, which is this? How would we compare? So benzene has conjugated double bonds, that's right. Or you could say alternating double bonds. That are conjugated, which allow the electrons to freely move, right?
This has something you can be used like for electricity.
So that it's not an open structure, it's a closed structure.
Please.
It's a closed structure. In an open structure, electricity can flow. So like if you had like a group of them.
And if we have solution of that, or not a solution, a liquid benzene.
Yeah.
What is those liquid?
It's a closed system. It's not an open system. Not outside of it. Name each molecule. What's this? A. It's phenol. So it starts with phenol. Serenade. And where's the CH3 from the phenol?
Two.
So 2-methyl phenol.
Lisa, that's what I said.
All right, what about B?
That's 2,4
No,
dichlorobenzene.
not 2-4. 1-3. Yep. Substituents get the lowest numbers possible. Carbon 1 does not have to be the carbon at the top. Carbon 1 is wherever your first substituent is, right? So carbon 1 is either here or here. Doesn't matter. If I said carbon 1 was here, then this is carbon 3. The 1, 3 is just saying that they're 2 away from each other. This molecule could be turned around, right? So it's 1, 3, dichlorobenzene. Okay, try another. What about this one?
One propyl.
Not propyl,
Ethyl.
not benzoic acid.
Ethyl.
Ethylbenzene.
Yes.
Ethylbenzene. So what were the mistakes? There are only 2 carbons here, right? CC, that's part of the chain. There's no benzoic acid, there's no OH. Ethylbenzene. There's no number because there's only 1 substituent. So it's just ethylbenzene. All right. So what would this one be?
Well, I think just
Okay.
It's
methylbenzene. That's its main name. So you can say 1 methylbenzene. So then it could be 1, 3, 5, 1 methyl. No, not 1, 3, 5.
or 2.
2, 4, 6. I heard you all say 1, 3, 5. Okay, 2, 4, 6. Methyl's 1. It's 2, 4, 6. Trinitro, right? 2, 4, 6 trinitro benzene. All right, what would its name be if it was the common name? Toluene, right? So wouldn't it be maybe trinitrotoluene? Have you heard of that?
No.
Hey,
Somebody has.
very nice.
Oh, is it the?
Or the chemical structure.
Let's think of
for
those
TNT.
letters.
Oh,
TNT.
That's TNT, the thing with the little thing that goes boom.
The thing with the little thing that goes.
Yeah, like with the little circles, they go boom.
wait, it's
TNT
that?
with the little cartoons and stuff, but no, that's real trinitrotoluene.
That's where we get
It's
to.
that molecule, yes.
Wait, does it go explode?
Yes, it's explosive. Yes. Yes, you can
Can
say
we
Joe
make
go.
it?
No, we cannot make it. Or-
Hey,
Daniel.
I was just about to.
Daniel.
We will not make it. We will not make it.
we are
The answer to
capable.
that question.
Can I go?
There is a capability of making that.
You could get like fire so like light it.
We will not make that. Is the answer to that.
Can I make it?
No, you should not. You should not make it. But anyway, so yeah, that's trinitrotoluene. Go ahead. I had a student. I have to show you all a meme at some point. I'm gonna post it on the Google Classroom.
Right.
Word. I have a meme a student made
Oh.
from it'll come to you about this. I have to pull it up.
Wait, is it like liquid or solid?
I believe it. Oh, it's pretty heavy.
It's a liquid though.
Yeah, it's
But
liquid.
it's a problem is that it sweats in the dynamite.
Huh?
A problem is that in the dynamite,
It sweats.
it sweats.
Like it's wet.
What's that?
meaning that it comes out of the dynamite.
Wait, oh,
Like over time.
they need to explode it fast. Even better.
All right, before we do anything else, I do have a wrap-up video for you on benzene, so I'm going to turn my mic off so that I don't hurt your ears. It's from one of my favorite